Good evening all. Welcome to the live session of Fundamentals of Convective Heat Transfer on week 10. We'll get started in a minute. So this week, most of the sessions is on so this week we have already gone through the lecture videos. The videos mostly focus on the numerical aspects of it. So instead of solving them analytically like we have been solving in the last couple of last 9 weeks or so. So in this particular week, we will discuss basics of finite difference method, and then we will see how to discretize a governing equation, followed by one of the prominent problems in this is something called checkerboarding problem. We will see what that problem means and how it is actually rectified. And then we will see the main difference between the other finite difference and in fluid dynamics. For example, when we are solving Navier-Stokes equation, the nonlinearity comes from the advection term. So we will see how to discretize the advection term, and then uh, we will see something called master and cell algorithm, which is one of the algorithms that is used to solve the Navier-Stokes equation. And since all of these are regarding the governing equations, we will also conclude with how the boundary conditions can actually be treated in all of this. Then we will take up some of the problems that we have already solved analytically before, and then try to get the solution using the finite difference method that is being discussed in this particular week. We'll solve the coed flow, the channel flow between two parallel plates. For fully developed case, you can also solve the developing flow as well, which I'm not taking up currently because of the limitations. I'm not sure how many of you are familiar with coding, but you can look up these problems. You can also refer to my videos on YouTube that are uploaded for computational fluid dynamics using finite volume technique, wherein I actually discuss these problems in little more detail using finite volume technique, where we actually use some C programming language to solve the problem as well. You can also use MATLAB, Python, whichever is your convenience. I have not actually discussed how to use commercial software, which you will anyway find many other videos available on YouTube. But we will discuss the main themes on required for this particular course. We'll solve a steady diffusion problem, and then we will take up advection problem, and we'll clear upon how to implement the upwind scheme versus central difference scheme. And with that, we will conclude this big session. So before starting the session, I hope you have already gone through the lecture videos. If you have any queries, please do unmute yourself and ask. And if there are no queries, then I will just give a summary of important points that are needed for this particular session alone. Yeah, I guess there are no questions, so we'll get started. So the idea in the finite difference technique or finite volume or finite element, any of this, is to solve a PDE. So if you have a general second order differential equation of this particular form, we have three different classes of problems, either parabolic, elliptic, or hyperbolic problems. Depending on the type of problem, the physics of the problem will actually change. So in finite difference, we approximate it using Taylor series in this particular way, and we try to get approximations for each of these terms. So we have, for example, if I want to write del t del x, it will be there are different schemes in which we choose that depending on the type of scheme you are choosing, depending on the way you are discretizing, your order will change. What this order exactly means is, so for example, if I have a mesh of a given size, if I reduce the mesh size by half, how much accuracy would I be getting in the in approximating that particular term? So for example, if I use either first order forward or backward difference, then it will be only of delta x, which means that if I use a mesh size of 0.1 mm and reduce the mesh size to 0.05, then my accuracy will be increased by the proportionately. So previously it was like 25%, now it will be 12.5%. So uh, the rate at which it approaches the true value will be linear in case of first order. However, if I use a second order scheme, then the rate at which the solutions will actually be close to the true solution will be second order or quadratic in nature. We usually use second order for space and first order for time. Instead of x, if you have t, then you'll be having the time differential. That's the only difference. But other than that, the basic idea is this. How do we get these different terms? Is basically for example, there are several techniques to get these terms. So depending on, you can choose which order of accuracy you want and accordingly get that level of accuracy by taking different points. So for example, I'll give you an illustration of how to do this. So for example, if you have share my screen. So let's say I want to approximate del square p del x square, or let's just write del square of del x square. I have different points. So let's say the points are f0 is at x equal to 0, f1, f2, and so on. So this is at x equal to, this is basically x, this is x plus delta x, this is x plus 2 delta x, and so on. Similarly, you will have the points on the other direction. So it will be f minus 1, f minus 2, and so on. This will be x minus delta x, this will be x minus 2 delta x, and so on. So the idea is, so for example, if you want a desired level of accuracy, you first write down these terms. So f0 will be f of x, f1 is basically f of x plus delta x. You can approximate it again in the same terms. And just write f prime, and so on. So what we are trying to do is now we are trying to get an approximation for this particular function. So we'll write del square f by del x square. Like similarly, we'll write for all other terms, whichever terms you have, f minus 1, f minus 2, so on. You write all of these terms. So now we will try to write something like del square f by del x square should be equal to c0 times f0, c1 times f1, c2 times f2, and so on. Whatever terms you have. So you can have c minus 1 times f minus 1, c minus 2 times f minus 2, and so on. So the idea is to determine these coefficients c1, c2, c0, c minus 1, c minus 2, etc. So if I have n such coefficients, I would require n such equations. So how would I get equations is by comparing the corresponding terms on LHS and RHS. So for example, on LHS, there is no f0 term. So when we do this thing, so we will actually take, we will group. So for example, when we are solving for similar terms, I would say coefficients. So for example, if I am trying to group the terms for f of x, on LHS, we do not have any f of x terms. So this will be 0. Equal to on RHS, I have a C0. For the second one, I'll have C1 plus C2, and so on. Similarly, if I try to group the terms for f prime of x, on LHS, I do not have any. On the RHS, however, I have a delta x plus 2 delta, sorry, C0 times, from the first one, I do not have any. From the second one, I have delta x. From the third one, I have 2 times delta x, and so on. Similarly, if I do for f double prime of x, on LHS, I have one term. On RHS for C0, I do not have any coefficients. From F1, I have a contribution here. From again F2, I have a contribution here. And so on. So basically what we'll be doing now is similarly you'll write F triple prime and all the coefficients. So depending on the number of unknowns you are having here, you will write that many equations. So if I have so basically if I need n coefficients, then we have to write n such equations. So basically, you'll get a system of equations of n equations and n variables that you will be able to solve and get the coefficient values. And if you do that for say for simple for whichever way, whatever term that is left after that. So after doing all of these terms, you would, for example, if here if I solve only for these variables, then anything higher up is actually gone, and then you will be end up with third order accuracy. Or if I end up with just C0 and C1, then with just this up to C2, then probably I will be ending up with delta x square instead of delta x cube. So depending on whatever, how many number of coefficients you choose, you will you will get that many terms into your expression for del square f del x square. So you can either write it in this way or another way. So for example, if you take a simple problem that is discussed in the lecture. So for example, if I want to approximate del square f del x square in terms of c0 into f0, c1 into f1 plus c minus 1 into f minus 1. Let's say if I want to do this, solve this particular problem. So I have three coefficients, so for which I'll require three equations. So I'll write f0 as f, f1 is basically f plus delta x into f prime plus delta x square by 2 f double prime and so on. Similarly, f2 is f plus 2 delta x f prime f double prime and so on. And we need f minus 1, for example, is f minus delta x f prime plus delta x square by 2 f double prime and so on. So now if I write the equation will be f double prime is c0 times f0 is f plus c1 times f plus delta x f prime plus delta x square by 2 f double prime plus higher order terms, and then I have c minus 1 f minus delta x f prime plus delta x square by 2 into f double prime. So if I compare the coefficients, so first let's say compare f terms. So on LHS we have 0, on RHS we have c0 plus c1 plus c minus 1. Now if we compare terms for f prime, it is 0, is c1, and we have minus c minus 1. And f for f double prime, on LHS we have the term 1 here, equals to for c0 we do not have any, but here we have 1 by 2 into c1 plus 1 by 2 into c minus 1. So these will be the three equations, and I have three unknowns that I should be able to solve. So from this equation we know c1 equals to c minus 1, which means from this equation c1 equals to c minus 1 equals to 1, then the summation will be equal to 1. So if both of them are 1, then we can substitute in the original equation to get c0 as minus 2. That here, yeah, there is an 1 by delta x square that will be coming here because of this delta x square that is over here. If I just take it on LHS, so I have to. Here, of course, there will be a delta x because it is 0. I have removed that one. So if we substitute it in the original equation, so we have our approximation del square f by del x square as c0 is minus 2 by delta x square, f0, f1 and f2 are 1. So we have f1 by delta x square plus f minus 1 by delta x square. This is what we were writing as f of x plus delta x minus 2 f of x plus f of x minus delta x by delta x square. So instead of using just these three values, you can use multiple values and accordingly use the higher order methods, whichever depending on your requirement of whatever order of accuracy you want, you can take that many terms into this equation and approximate this. But usually it is not recommended to go beyond second order, because as you go higher and higher orders, you will have oscillations coming into picture. You can try it out once and see what happens to get an intuition of what actually goes on into the problem. But the basics are this. So whatever order you want, you can get it in this particular fashion. So once we have that, the idea is to use this for a particular in our problems. So one example in our problem is we have to discretize, for example, the conduction equation, the unsteady conduction equation as this. How do we proceed with that? This is already discussed in the lecture video, so I think it should be fairly straightforward. We have the unsteady term given by, this is the volumetric heat generation by rho Cp. So if I have to discretize this, so we have to come up with a notation. So the notation goes as, we can use the forward time explicit method. So Tn plus 1 at a given vertex I minus Tn at the same vertex divided by delta T is alpha times, for the second order we have just derived this. So here, depending on which time you use, you have different methods. So I'll be using something called explicit method, where you take the previous time step values. This will be Tn I plus 1 plus whatever volumetric heat generation you're having at that particular cell divided by rho Cp. Then we have to solve this set of equations. But this would be the discretization part. Like this is one way of discretizing. However, instead of this is not the only way to discretize it. Why should I take only these values at n? You can take these values at n plus 1 and solve it in a different way. And why should I take only at n plus 1? You can also try other combinations. There are other methods wherein you take a fixed weightage of the previous one and like some constant times the previous one plus 1 minus the constant times something like some r times tn. There are different ways in how to select this R and stuff, but the basic idea is the same. The idea behind this discretization is to convert the original PDE into a set of equations like this. So once you have this set of equations, so the main idea is in all these numerical methods is first you have a PDE, the governing equation. Once you have the PDE, you first discretize your domain. So basically convert your continuous domain into a discrete domain. So inside the discrete domain, you take the same governing equation, but now the governing equation will be at each and every individual point. So each equation will be essentially coming to one point. So each point will essentially have to satisfy the governing equation. So every discrete point will be now my one equation. So if I have n discrete points and I'll be applying the governing equation at each of these points, so I'll be getting n different equations. And I have n unknown variables, so I should be able to solve this system of equations and with the given number of unknowns. That is the whole idea in all these numerical techniques. So the way you convert from continuous to discrete is how we have different techniques in it. You either use finite difference, finite element, finite volume. All of these are different ways to do that. But once you discretize them, you have to solve this set of equations. Again, depending on the type of solver you are having, you can have direct, indirect, iterative solvers, whatever it is. So you have to come up with a solver that will actually take up all the system of equations and solve them simultaneously to give you the values of p or u, whatever is your variable of interest. I don't think there are any questions in this. So the major problem we have in the normal way when we solve it is something called checkerboarding problem. I hope you have already gone through the Excel video, so you'll be able to answer this question. Which of the following do you think is the reason for checkerboarding problem? Is it because I am using central differencing for the pressure term in momentum equation? Or is it because I am doing a central differencing for velocity term in the continuity equation? Or is it because I am storing velocity and pressure at the same grid points the problem is coming? So which of these is true? Which of these is the true reason for checkerboarding problem? Okay, so what exactly is this checkerboarding problem? So if you see the continuity equation, we have del u del x, let's say in 2D. So if we have this equation and I try to discretize this, we can write this as u I plus 1 j. So my grid is something like this. So this is my ij, this is I plus 1 j. So I basically is the index along the x direction and j is basically the index along the y direction. Sorry, let's say this is the negative direction. So let's put j minus 1 and this is j plus 1. Yeah, you can have similar terms here. So this is I plus 1, j minus 1. This will be I minus 1, j minus 1. This will be I minus 1, j plus 1. And here you will be having I plus 1, j plus 1. This will be the different indices for the cell location. So if I'm storing velocity at the central point, so if I write del u del x, so that will be, this is a second order technique, second order central differential. And similarly, I'll have del v del y. So in order to solve this problem, if for example, while you are solving the problem using an iterative solver, then what could happen possibly is you might end up in a scenario where these velocities are actually equal to each other. So if, for example, ui plus 1 equals to ui minus 1 and vij plus 1 equals to vij minus 1. So if this particular condition is satisfied, then this equation will essentially mean 0. But does it mean that we have a solution that satisfies this original equation? It's a question that we need to answer. So if you look up the same thing in the momentum equation as well, we have a minus del p del x term, which again we will compute like pi, since there is a minus, so this will be pi minus 1j minus pi plus 1j divided by 2 delta x. So what could happen is if I plot as a function of x, let's say if I plot pressure as a function of x, so at this point let it be 0, but in the next grid point, let's say it has a high value, and the next grid point it has a 0, next grid point it has a higher value. So these are the grid points. So what if pressure is oscillating something like this in the space? So if pressure is oscillating like this, then obviously from a physical point of view, this cannot happen. If this happens, then the derivative should not be equal to 0. But the way we have discretized it, so what it would do is, for example, if this is my ith point, it will calculate, in order to calculate the derivative at this point, it will take pi plus 1, so this value minus this value. This value minus this value is basically 0. So what it would think is the pressure gradient is 0. And then what would happen is this would get propagated into my momentum equation, and the momentum equation velocity will not be updated because there is no pressure gradient. And in that case, if velocity is also like this, then velocity will also be not updated. That is the main problem, which we are calling the checkerboarding problem. So the idea to solve this is, I don't want both of them to be 0 at the same time. So what we will do is, instead of calculating gradients in this way, we will calculate the gradient for velocity at different points. So if these are the pressure nodes, I will use the next one to be the velocity nodes. So the idea here is, because I'm using different locations to compute the gradients, the chances of both of them having the things like this is wrong. So if pressure is like this, then most likely velocity will also follow some similar pattern. And say for example, velocity also follows a similar pattern. So if your velocity is increasing, decreasing, and let's say your velocity is like this. So if you have a velocity profile like this now, and I am not using the same grid, but I'm using a different grid here. So then, in order to calculate the velocity gradient, I would be using velocities at different points. Because I'm trying to update the velocity here, which is not 0, even though the pressure gradient is 0, it will try to see that there is a different value of gradient over there. So your continuity equation will not be 0. Or so for example, if I have to calculate del u del x in this grid, let's say this is my u, if it is following the same pattern as pressure, let's suppose if both of them are following the same pattern. So if I calculate del u del x at this particular point, sorry, del u del x at this particular point, let's say this is my ith cell, this will be I plus half, this will be I minus half. So I will be using, so what would be my equation for gradient here? or we can use different approximation. So if I use an approximation like this, let's say this is first order, is it first order or second order? Yeah, it is second order, but in terms of delta x by 2. So okay, if I use an approximation like this and use the velocity value of ui plus half and ui minus half, how do I get ui plus half and ui minus half? So because I'm using ui plus half and ui minus half instead of versus the previous one, so ui plus 1 minus ui minus 1. So this versus this is what we are trying to compare. Let's say this is 1, this is 2. 1 versus 2 is what we are trying to compare. So this is 1. And what would happen in the second case is because I'm using uh, this equation, the chances of if a checkerboarding happens, then it will be between ui plus half and ui minus half. If both of them are equal to 0, only then it will be turning out to be 0. So what happens is this is I plus half, I minus half. So whatever value that is coming here, yeah, I think okay, I think I kind of reverse the situation here. We'll get back to this in little time. But the basic idea here is what would happen, what we would like to expect now is your profile becomes something like this. So that both of these cannot be simultaneously be zero at the same time. I'll give an illustration with a problem, then it will become more clearer. But the basic idea here is the main problem is happening because we don't want both the continuity and the pressure term in the momentum equations to be zero at the same time. So just by considering this alone or this alone, the problem of checkerboarding cannot be removed. So the way when we introduce the staggered gate concept is to ensure that even if one of them is zero, the other one will still be non-zero and iteration continues. So for example, even if you get a velocity field which has checkerboarding pattern, but because there is still momentum equation that you have to solve for, in the momentum equation, the pressure will not be zero and that will let the whatever algorithm is using to solve this particular problem to iterate more to eventually find a better solution. That is the main idea behind the staggered gate technique. Yeah. Uh, I'm not sure if it is 100% clear, but maybe I'll try to make it better when we take an example problem and then it will be more clear. So the most important part in the Navier-Stokes equation is the advection term. And when we try to, how do we get equations for this advection term is what we will see in this, right? So the idea here is again, say for example, if you have a term like del x of u into 5, where phi can be any quantity, it can be either velocity, temperature, concentration, or any other quantity of whatever is in your particular transport quantity that you have. So how do we do this is, again we take the same grid. So this is my I plus 1, I minus 1, let's use different index for I plus half and I minus half. The velocity is being done at I plus half and I minus half. So these are the coordinates where velocity is being stored. So what this would eventually become is u phi evaluated at I plus half minus u phi evaluated at I minus half by the difference between them, which is delta x, right? So the question now is, what should be the values of this u? So this is basically ui plus half into pi plus half. What we need to find now is what are these values of ui plus half minus half pi plus half and pi minus half. Because the actual velocity phi is the speed, whatever transport quantity that you're using is stored at the cell centers, which is this I plus 1, I minus 1, I plus 1, etc. I plus 1, I minus 1. but I need the values of these quantity at I minus half and I plus half. So what value should I be using? That would be the question. So for example, for ui plus half, you can always use the average velocity in 2D. So this will be ui plus 1 by 2. And similarly for the other one, I can use ui plus ui minus 1 by 2. I can use the mean velocity. So the velocity at this particular point is the average of the velocities at these 2 points. Similarly, the velocity at this point is average of these 2 points. But what we do in the upwind scheme for this pi plus 2, so if I have to find the velocity of phi at, if I want to know what is the value of phi at this I plus half, so depending on the velocity profile, I'll choose this value. So if the velocity is positive, this I can take as either phi or phi plus 1. And this choice will depend on the actual velocity u that is there in that particular cell. So if the velocity is positive, which means, for example, if this is my positive direction, if the flow is happening in this particular way, then what we are saying is the whatever that P, instead of P, you have temperature here. The temperature here, basically, because there is advection term like this, the flow is happening in this particular direction. The temperature here can be the information about the temperature here is coming from the temperature in this particular cell, because flow is happening from left to right. So when u is positive, we will say phi plus half is equal to phi. So this is a conservative estimate. In a similar way, if for example the flow is happening in the reverse direction, so if it is happening from right to left, then the temperature here would actually be carried by the temperature that is at this point. This will be phi plus 1 if ui plus half is negative. So the same equation, whatever I have written here, can be written in a more, like in just a slightly different form. So let's say I can write this as into ui plus half. Let's say I want to take the combination of these terms. So I can write this as something like phi. You have to get the value of phi when ui plus half is positive. So when this is positive, this product should be phi times ui plus half. Otherwise, it should be phi plus 1 times ui plus half. Right? So whatever I've written it using this particular function way, we can write it in one single statement saying that ui plus half times phi plus half is basically phi times I'll take ui plus half plus absolute value modulus of ui plus half by 2. If I write it in this particular fashion, so if ui plus half is positive, then the summation will be 2 times ui plus half divided by 2. So this will be ui. So I will be recovering the same equation, pi into ui plus half. If, for example, this is negative, then this quantity will just go to 0, and then I have to use the second term. We will use the same logic there. So we'll write pi plus 1 because it should be negative. So we'll have a negative sign here. So it is basically a weight summation of phi and pi plus 1, and the weightage will depend on the sign of that particular sign of the velocity at that particular point. So if I just rearrange the terms, what would I be getting is, yeah, we can rearrange the terms. So let me take ui plus half as common. Similarly, you can write for the other one as well. So if you were to write it the same way for the other one, it will be phi minus phi minus, oh sorry. So ui minus half and phi minus half will be ui minus half. Instead of I plus 1, we'll be having I minus 1 here. That would be the only difference. So the another term that we are adding here is the other way to do the same approximation. So this is one way. So this particular one is called the upwind scheme. This is not the only way you can do this particular one. So you can also always approximate, just like how we have approximated ui plus half to do this. You can also take phi plus half to be phi plus pi plus 1 by 2. This is also one kind of approximation called central approximation. There are advantages and disadvantages both these methods. It depends on your particular problem. Sometimes using upwind it may not be suitable. Sometimes affine is more usable, but the better way is this is physically more meaningful in the sense that when we are doing an average on both the sides. So for example, if the flow is happening in this direction, and in order to estimate the value of temperature, for example, in this point, you are using temperature from the next cell. But physically, information is flowing from left to right. So this particular taking in this way is not physical. So taking an average of something that has no influence on this physically is not meaningful. But when we have weak advection terms and when diffusion is dominant, so when we have scenarios where the effect of advection is not very significant, then in those scenarios, what happens is information will flow in all the directions. Diffusion basically means it happens from all the directions. So in those scenarios, what could happen? It would be better to actually take the other one, I plus 1 plus I, instead of taking in one direction, because this effect is less pronounced than the other one. But it depends on the physics of the problem. Usually we'll go with the affine scheme, which is, of course, affine is linear, first order, whereas central is second order. There are other things that we have to consider as well, but for now we can, the idea is to get you understand how to implement this yourself. If that part is clear, I think we can go ahead. The next scheme is, of course, you will not use any one of them. So you have to use a weight combination of both affine and central. Depending on the value of R you choose, it will either become an affine or a central. For example, if I choose R equal to 0, it will become central. If R equal to 1, it will become affine. Okay. The next algorithm that is finally proposed in the lecture video is something called Mark-Wenzel algorithm. This is to solve the entire equation. So once we have discretized our diffusion term, advection term, and the time domain term, the only thing that is remaining is solving all these three equations simultaneously. So we have continuity, x momentum, and y momentum in case of 2D. So if I have to solve all the equations simultaneously, how do I go about it? That one particular technique is this Mark-Wenzel algorithm. So which of these statements are true in that particular algorithm? Continuity equation is discretized at current time step. Momentum equation is solved by assuming pressure from previous time step to get velocities. Pressure corrections are assumed to be zero in the neighboring cells, and corrected velocities are obtained by solving the momentum equation with the corrected pressures. So if you see the flow of how this algorithm works, you start with your momentum equation first. We already assume a given velocity and pressure profiles, and then what we do is with the assumed profile, you integrate one time step. So from the current time step at t equal to 0, initial conditions have to be provided. So from the initial condition, you move one step ahead, and once you are done one step ahead with the assumed pressure, obviously whatever velocities you're going to get are not accurate, are not the correct velocities, because while solving for the momentum equation, we have not accounted for the fact that the velocity has to satisfy the continuity equation. Now we have to somehow incorporate that information into this. So the first step is you get an intermediate velocity, which let's say we call predicted velocity. So we have to correct the predicted velocity. So we'll assume that the corrected velocity or the actual velocity is whatever velocity we got from the previous step plus some constant time p prime. And in order to solve for this p prime, which will tell us how much to increase our u, we will use the continuity equation. Because u has to be the actual solution, the continuity equation should be satisfied for u, which means del dot u should be equal to 0. So from which we have this equation here. So del dot u bar plus k del prime equal to 0. So because we already have this u bar, we can calculate the divergence of it and we can solve for this particular equation. So basically this will become like if you take a derivative again, so this will eventually become a Laplace equation that we should be able to solve for. Or maybe there is a correction here. Sorry for the correction. So it would basically be something like this. The corrected velocity you will take as whatever velocity you got from the previous step plus k times del p prime, something of this sort. When you take the divergence of u, because this u should be the actual velocity, we want this term to be 0. This is where the continuity equation is actually being used. Now we will solve for this equation and get p prime. Once I have p prime, I can substitute that back in this. I know u tilde already, from which I'll get my velocity profile. Because I have velocity, now I'll also update my pressure term, whatever I have previously plus this p prime. So you start with an assumed pressure profile, solve the momentum equation, and then update the velocity. There should be a del term here that is missing. I'll correct this before the final update. And then we will solve for this equation, continuity equation together. In this when you solve this continuity, we'll have a Laplace term here. Instead of del, it will be del square. You have to solve for p prime. Once you have p prime, you can get u and p, and then you keep iterating till For example, if it is a transient problem, then you will keep iterating till whatever time step you want. If it is a steady state problem instead, you will just, this term will be eliminated. You will keep doing till your convergence criteria is met. The convergence criteria will usually be, for example, if the velocities are not changing beyond whatever epsilon tolerance that you give, or it could be in terms of the tolerance in your quantitative equation, or it could be in, sometimes in case of steady state problems, you might have to give other convergence criteria. For example, if you have if you're interested in finding temperature in a room or something, so you can also monitor temperature as your solution progresses at a given point and see if that temperature is changing beyond a particular point. So what does that mean is, even though your solver is trying to solve the problem, there is no much improvement in the particular quantity of your interest, so there is no point in solving further. So you can stop your iterations at a given point after that particular point. Boundary conditions, we have basically digitalized normal type of conditions where from a flow point of view, you'll be either given velocities, or no slip is basically means zero velocity, or you will be given outflow velocity where the velocity gradients are essentially zero. Similarly, for temperature, we will either be given a given temperature, or you will be telling that you will be told that it's an adiabatic case, or it can be a convection case, where mixed convection kind of thing, where the heat transfer coefficient will be given. So we'll just see the heat transfer coefficient part. So let's say if this is my cell, so this is my boundary cell 2P, and it is exposed to ambient with heat transfer coefficient H, and let's say T naught is the reference temperature, and this is my last but one cell Ti. So the idea here is you have to the heat transfer should be balanced. Like if I apply heat balance here, the heat that is going out is minus K times del T del X. So I can approximate del T del X with the first order difference here. So that will be Tb minus Ti by delta X should be equal to H into Tb minus T0. This term, let's call it H external, and this particular term here that we have, we can call it as H internal. So I can write an expression like this. And what we are interested in is finding this TB, because I need that in order to be able to solve the equation. So you can get TB. Okay, the flow is happening in this direction. So if you just rewrite the equation, so this will be minus K times, assuming that it is in this direction, this temperature should be higher than this. There will be a minus here because of this minus K by delta X. So if I group the terms together, so I'll have TB is He times T0 plus Hi times Ti by He plus Hi. So this would give me the boundary temperature, which I will use in my equation subsequently. We will actually solve a example problem where you will see that more clearly. Are there any questions up until now? Yeah, there are no questions, then we will take up the same problem. These are meant to be a demo problem, so we'll have an understanding of how to actually take up these problems and solve on your own. The first one is a co flow problem where you have a fully developed flow between two parallel plates, which we have already solved this using analytically. We already know that the solution is going to be linear. Let's say if you have to solve this using the technique that we presented just now. Again, we will use the same tool that we have been using before. So first we will define the number of grid points. So we have to discretize the domain. Our domain is only along the y direction because it is a one-dimensional flow field. So we have the number of grid points I have given as 11 grid points, and delta y is 1 by number of grid points minus 1. So what we are trying to do now is we have a co-ed flow, and this is the direction that I am trying to solve for. So we will discretize the y domain, say from point 1 to 3 and so on. Or I'll just put, so all these are the interior points, and these will be my boundary points that we are trying to solve for. So My first equation would be writing the discrete form. So my governing equation for this fluid flow is we have in entire, if you take the momentum equation, u del u del x. We are assuming it to be fully developed. So all the terms along the x direction will be 0. So this will be 0. And we are assuming there is no pressure gradient. Because V is 0, this will be 0. And fully developed, this will be 0. So all we are left with is only one equation, that is d square u dy square equal to 0. And if I use the discretization technique that we have just discussed a little while before for this, so this will be u into I plus 1 minus 2 ui plus u minus 1 I delta y square should be 0. So this is the equation I have written here. So ui plus 1 minus 2 ui plus ui minus 1, and just remove the delta y square on the other side, so that should equal to 0. So this equation we have to use for all the cells except for the boundary cells. So I have kept the index from 2 to n minus 1. Is that clear? So this equation will be true for all I equals to 2 to n minus 1. Now for the cells 1 and n, we have to use the prescribed boundary conditions. So in this particular case, so this is a 0 first cell, and so on. This is my nth cell at equal at u of 1 should be equal to 0. That is a no slip condition. Similarly, for nth grid also we have to have no slip condition, because the plate is moving with a constant velocity. You have to keep that velocity here. I've assumed it to be 1. Now I have my boundary conditions and the equations. So I'll join both of them. So I'll have, so how many equations do I have here? 2 to n minus 1 will be n minus 2. Sorry. Here I have 2 equations, and here I'll be having n minus 1 equations. So in total I have n plus 1 equations. So I have n plus 1 equations, and my original, sorry, so 2 to n minus 1 is n minus 2 equations, and I have 2 boundary conditions. So in total I have n equations, and I have n unknown variables. So this is a system of equations that I will be solving for. You can use any solver of your choice. If I join all the equations, so they'll appear something like this. You can either you can convert this into a big matrix and then solve using any of the linear algebra methods, or you can solve it iteratively. Any other technique is there, but I'm not going into how to solve this actually. So we'll use the method that is already available in Mathematica. So it solves all this set of equation. It gives me the solution where all these values will be given to me. So I'll just take up the solution values and then make a plot of it. So we already know how the plot should look. We know that for a fluid flow it will be linear, so that is what we see here. So if the velocity has increased, let's not see the solution. So for example, instead of giving the velocity to be 1, let's say I give 10. So you can see how the velocity at the top at y equal to 1, the velocity has increased to 10. So this is what this is something we already know before itself, that the velocity will be linear in case of a fluid flow. This is just to demonstrate that you can use the technique that we have been discussing now. So all we are doing now is we are writing the equation, and we are writing this equation at each and every grid point, and we have to give the explicitly specify what values to use at the boundary conditions. And with these values, you will be able to solve all the, like, combine all the equations together and solve them in one go. That should give us a solution. Are there any questions in this? Yeah, I guess there are no questions. Then we'll solve another problem. Let's say you have the channel flow problem. Again, this is a parallel plates, but then here we have, if, let's say the velocity u equal to 0, and then we are solving for with a constant pressure gradient, and let's say the pressure gradient is 1 Pascal per meter. All the values are taken to be 1. So if I were to write the governing equation for this, so again it would be similar to whatever we were having before, just that the only difference is now we have a pressure gradient term, so this will be minus dp dx equal to 0. Again, this is something that we have already solved before, so I'm just telling you that this is a constant value. So you can take that to be some constant, d square u dy square equal to some constant c1. You can get this constant from whatever values that are provided, and you have to solve for this. Provided the boundary conditions are at y equal to 0, the velocity has to be 0, and at y equals to 1 also, the velocity has to be 0. And you have to solve this particular equation. Similar as what we have done before, You discretize this and solve for it. So just like before, you take the number of grid points, pressure gradient, whatever value specified in the problem. So your discrete equation is mu into ui plus 1 minus 2 ui plus ui minus plus 2i minus 1 by delta y square plus pressure gradient term I have put minus here because we have minus del p del x. So if this is minus, then it means the pressure is actually increasing as you go along the x. Then the velocity will be positive. If it is positive pressure gradient, which means pressure is increasing along that direction, then the flow will actually be reversed. So this discrete equations is basically in the interior cells. So you do it from I equal to 2 to n minus 1, and the boundary conditions are at I equal to 1, we have v should be 0, and similarly at the last grid point also velocity has to be 0 because both the plates are stationary. Now we will join both these equations and boundary conditions together and solve for them simultaneously. So what is the velocity profile that you would expect in this case? Yeah, it should be a parabolic profile. Let me see what it is. The velocity profile appears parabolic here. And let's say if you want to calculate the mean velocity and maximum velocity and see how they will compare with each other. So you know what is the what should be the value of maximum and mean for this particular channel flow? Yeah, we have already solved this before, so it should be 3 by 2. So for this particular point, it's close to around 1.5, which is close to 3 by 2, a little off. So in order to get more accurate, you have to consider more and more grid points. This is what we were discussing. So the way of the discretization that we have seen here is second order accurate. So let's say if I double the number of grid points, you can see it has already been accurate up to 2 decimal places. So you can keep refining it more and more. So if you have 40 grid points, you will see it up to fourth decimal place. So from second decimal to fourth decimal. So this is what we is meant by the second order accuracy that I was talking about some time before. As you take more and more grid points, this will become closer and closer to the 3 by 2 that we got from the analytical solution. This is something called grid independence that has to be done for all of your numerical simulations just to be sure that your solutions are consistent. So by refining more and more, you should be able to approach closer and closer to the actual or the true solution. The next we will consider a study diffusion problem. So let's say the idea here is to make you understand the different kinds of boundary conditions and how to implement them in your whatever code you are trying to develop. Let's say first we will solve with we'll first solve with the case of upwind scheme. So we will have to first discretize the governing equation. Let's take the governing equation. So the governing equation is del square t del x square plus del square t del y square equals to 0. And if I try to discretize this, this will be these are the set of equations that I'm trying to solve now with the whatever boundary conditions I have. So let us first solve study diffusion. So this is the equation I have written here. Here, whatever equation I have just shown you for all the grid points except the boundary cells. Now at the boundary cells, we have to give different boundary conditions. So on the left boundary, we have the condition. So this is my domain. This is my left. Here we have H and T naught. Here I have a prescribed temperature. Here we have adiabatic condition, and we are trying to solve this. So if I were to write mathematically, on the left boundary condition is T of for all the values of j. Sorry, this is a different one. Yeah. For all the values of j uh, from here to here, for all the values of j for I equal to 1, it should be equal to T left, whatever is specified. And similarly for the top boundary, for all values of I at the top boundary, j will be ny, should be equal to, because the gradient has to be 0, it should be equal to whatever is the value one step below it, ny minus 1. Similarly for the bottom boundary, ti at 1 should be equal to whatever is on the top of it, which is I equal to 2 for all the values of I. And for the right boundary, we have the mixed convection boundary condition where minus k into k by delta x into whatever quantity that we are having here should be equal to h into delta t. Now I will combine all these equations and then solve them just as what we have done before. The only difference now is now I have equations in both x and y directions. So when I have to flatten them, it will be like double. So for example, if I have 21 points here, so the total number of equations that I will be, previously I will be having only 21, but now it will be 21 square. I'll be having around 400 equations or so that I have to solve for. And if you plot it like just as you would expect, the plot should have the temperature should gradually increase from left to right, where on the leftmost end you have 350 Kelvin, and as you go to the right, you keep increasing. So from 350, as you go to the right, okay, the temperature is 300, so this will get cooled down. So here temperature will be close to 300, and the top and bottom are adiabatic, so there won't be any gradients or anything like that. So what you would expect is you want to have straight lines. So you'll expect some straight line contours here. It's taking a bit more time to solve for some reason. Maybe I'll post the solutions. This is not actually ideally suited for this kind of problems. You can use the Python or MATLAB to actually solve this in a much efficient way. The only reason I'm using this is to kind of show you the equations and how to put them together. I wouldn't recommend to actually solve the problem using this particular tool. Taking a little longer than it was supposed to take. So this is the plot we are going to have. So as expected, the temperature here will be very high, and as we go towards the right end, the temperature will gradually reduce and it will be close to 300. This is a straightforward one. Now let's say the next problem is where you have a little more a step ahead, wherein we say that the velocity is actually there. Instead of having pure diffusion, we have an advection also in place. And for us, let's say the velocity is actually given to us. Ideally, when you are solving a couple problem, or let's say you have a normal problem where you have to solve for the momentum equation, get the velocity profile, and then you will go for the temperature equation or the energy equation. But let's say the velocity is already given to us somehow. So someone actually solved the momentum and continuity equation and gave us the velocity profile. And let's say the velocity profile is I cap plus 2j cap. And I have for that velocity profile, I have to solve the same problem. So what do we expect now? It will be the similar, right? So the only difference is because now there is a horizontal velocity, what would happen is this temperature will be propagated more downstream. So as this velocity keeps on increasing, what we would expect is eventually this entire thing will actually become close to 350. Or just show you on, let's say if you are solving it up one, everything would be similar to whatever we were doing before. The only difference here is the way we approximate del T del x and del T del y terms in the advection part of the equation. So in the advection part, so del T del x will approximate with Tij minus Ti minus 1j. So this is because we know the velocity is positive. Or let me just try to explain that to you. So this equation remains same, just that now I have an additional term u del T del x. We have something like this. So in order to approximate del T del x, we will write this as, let's say these are the grid points, just like before whatever we have in. Del T del x can be written as T equal to whatever we have derived previously. The only big thing is how do I get Ti plus half? So this is I plus half, and this is I minus half. So we know that velocity is given to us. So we know u is 1 and v is 2. And because u is positive, the flow is like this and like this. So it will be something like this. Because u is positive in this particular direction, at this particular point. So what we will do now is we will approximate Ti plus half with the cell that is upstream of it. That is exactly why we call this upwind scheme. So the cell that is upstream is because flow is happening like this. The upstream cell is Ij. So we will use Ij for that. And similarly for the other one, for this particular cell, the upstream will be the one that is to this side. So that will be Ti minus 1. Similarly for the other direction, Tij plus half will be Tij. J minus half will be Tij minus 1. So this is the upwind scheme. So if I were to use a central scheme, so how would that be? So I would have to just take something like this. This would be the central scheme. So if I just write down those equations, so I have u into Ti minus 1 and Ti into Ti minus 1 for the v component Jj minus 1. And the diffusion terms would be similar to whatever we have written before. Boundary conditions are also similar. So it is still taking a little bit time, so wait for a little bit time. In the meanwhile, do you have any questions? Taking longer than we should. For some reason, yeah. So as you can see, if you compare this with the previous one that we got, the previous one was this one. So you can see the difference between these two. The width of this particular one is little higher than the one that you can see here. And this is essentially because we have a velocity that is here. So what that is doing is that advection is actually carrying the temperature little forward. So for example, if I increase this to 10, then you can see the difference clearly. You can see how much it has propagated. So as the advection velocity increases, this would actually get propagated more and more in downstream. This is clear, right? So what does it mean when to have a velocity that is 10? It means basically I have a constant temperature 350 here, so it is as if I am blowing a hot air. So if the velocity of hot air increases, then the entire room will actually become more and more hotter. Of course, here we have top and bottom as adiabatic. So even though I change V, nothing should change. You can check that as well. So if I put V equals to 20, for example, nothing would change. The only deciding factor here is U and not V. And that is essentially because I have prescribed the temperature only along this. So for example, for some reason, at the bottom boundary, for example, if I have a cooler air that is coming from the bottom, so how would I change? Is bottom boundary previously was adiabatic, so I kept Ti1 equal to Ti2. But instead of Ti2, let's say it is constant at say 280 Kelvin. So this is basically trying to cool the room. So then what would happen is you would expect something like this. There will be a cold blow of air. Of course, there is no gravity here, which I should have included, which you can try later. But let's say keep a smaller velocity so you can see it more clearly. So you can see clearly that it tries to cool the room, but eventually the room will actually like here it will be very hot, and then gradually it will decrease, and it eventually is 350. And here the temperature will be lower than whatever is the outside temperature 300 Kelvin. These are all physically correct, but then again you have to do the mesh independence where you have to vary this mesh size, try to increase the number of grid points, and see that your solution will actually converge. These are the common steps that you do in any of the numerical problems that you might be solving later if you are into this domain. Now the same problem you can solve with the central scheme as well. The only difference would be this one. So here you were using Ti minus Ti minus 1, but here it would be Ti plus 1 minus Ti minus 1 by 2 delta x. So this is the second order approximation. This is only first order approximation. So with this second order approximation, again, once you solve it, you would get the same solution as before when we are using U equal to 1 and V equal to 2. There shouldn't be any difference in the solution as such. If you are interested in more, you can actually take up some CFD course and you will actually understand what are the problems with the, say, for example, the upper scheme or the central scheme. One of them is more diffuse than other, while other one is discussed. These are other terms that I would not like to discuss in this particular course, but I think you got an idea of how to actually implement this. I'm not taking a problem where you actually have marker and cell over the minute because that would be more involved in little bit into the coding part. So apart from that, are there any questions? Yeah, I guess there are no further questions. Then these are the problems I have for this week. Because it is more of the numerical part, I cannot actually take up any coding problems. I do not expect anyone to know coding for this particular course. But if you do have any queries, you can reach out to me. And next week we will be, so I'll quickly summarize whatever we have discussed in this week. So we started out with the basic finite difference scheme, and then we actually learn how to discretize the problem. And then we discuss what checkerboard problem means and how staggered gate helps to solve that particular problem. Finally, we try to see how to discretize the advection term of your Navier-Stokes equation, and we just showed the pseudocode for marker and cell algorithm, followed by the boundary conditions that are there. Eventually, we discuss some sample problems using Mathematica for Couette flow, channel flow, static diffusion, all these problems which we have already solved previously using the analytical solutions, and then we now we compared with the for the case of Couette flow, we compared the for the case of parallel plate channel flow, we compared the solution with the analytical solution. We have seen that both are parabolic in nature, and as you increase the number of bitcoins, both are approaching the same solution. And finally, we solved we took up a problem where you discretize using upper and central schemes, so you can understand the difference between these two schemes. Of course, in both of these schemes, we assume that the velocity field is actually given to us. You don't have to solve much of it. But when the velocity field itself is an unknown, then you have to iterate again. So you have to assume a velocity field, solve for it, and then again iterate, solve the momentum equation, get it, and we keep doing that, which we have not taken up in this particular case. Yeah, so there are no further questions, and we will end the session for this week. So next week we'll be starting turbulent flows. We'll start with the Rance equations, and then we'll take up some problems. Please go through the lecture videos. During this session, if you have any queries, we will go through the derivations. Otherwise, we will skip the derivation part. We'll probably take up some problems that you can solve for. Yeah. Yeah. There are no questions, and we will end the session for today. Thank you for joining. We'll meet again. And to note that we'll be having one extra session on towards the end of towards the mid of October, on say October 11th. Instead of having from 5 to 7, we'll be having 1 hour extra, say from 4 to 7. So we'll be having 3-hour session. So that would be the final session for this particular class. So if you do have any queries throughout the entire course, you can bring it up in that particular session and we will take up them. And if for some reason I'm not able to take up during particular session, you can write out to me later and I can discuss with you personally after that particular class. Okay. Thank you for joining. Yeah, I'm ending the session for today.